Hello everyone. In this paper we propose a new approach to learned optimization. Let us assume that we are given a scalar objective function L and we seek an n-dimensional vector x that corresponds to a minima of L. This task is often solved using iterative optimization approaches that start with initial value of x0 and then update x using a function u that depends on gradients along the optimization trajectory. For example, for the gradient descent and gradient descent with momentum, the update function u corresponds to the following expressions. In our learned optimization approach, we follow a similar iterative strategy, but use neural network to parameterize u that in addition to gradients also takes other features as input. Our main contribution is a new architecture for learned optimization inspired by the classic BFGS approach. In our model, the update function u is composed of a feed-forward neural network that outputs log learning rate and update direction, and a transformer model that generates preconditioner. We jointly train both networks on a dataset of training optimization problems. Let us now discuss the related work and provide more details of our approach. We will focus on a few examples of related work here and refer to the paper for more comprehensive review. The first class of related methods represents update function u as a multi-layer perceptron that is applied independently to every dimension of x. This resembles first-order iterative methods such as gradient descent and Adam that apply the same update formula to every dimension. This class of methods can naturally generalize to problems of variable dimensionality and uses metaparameters sparingly since they are shared across dimensions. The drawback of these methods is that they do not allow coupling between updates of different dimensions, which is potentially suboptimal. In the second class of methods in the literature, the update function is modeled as an MLP that jointly modifies every dimension of x. This allows to couple updates across dimensions, but requires dimensionality of x to be the same at training and test time. As an improvement over these methods, we propose an approach that can be applied to optimization problems of variable dimensionality without retraining, while coupling updates across dimensions. However, this comes at a cost of additional computation that, similarly to BFGS, grows quadratically with the number of optimization dimensions. Our approach is therefore best suited for problems with an objective function that is relatively expensive to compute, so that additional computation spent on update step is amortized by a reduced number of update iterations. Finally, we would like to mention a recently developed learned optimizer Velo, published concurrently with our work. Velo is specifically trained on the task of optimizing neural network parameters and couples updates between parameter dimensions using RNN with LSTM units. Conceptually, Velo has similar advantages to our approach, but has not been evaluated on tasks considered in our paper. Let us now discuss our approach in detail. As we mentioned earlier, we represent the update function as a product of preconditioning matrix and a vector of per parameter updates. Our approach takes the current parameter values and objective function gradient as input, and as a first step augments it with a set of other factor features and other features such as momentum and second moment values. It then computes log learning rate and update direction for each parameter using a simple 3-layer MLP shared between parameters similarly to the work of Metz et al. To compute the preconditioner B, our approach applies a stack of transformer encoder layers to the input features, which enables coupling between parameter dimensions via self-attention. We then apply a linear mapping to the output of each layer to obtain n-dimensional vector u, which is then used for rank 1 updates of the preconditioning matrix. Our approach incrementally updates the preconditioner, similarly to how BFGS incrementally updates the inverse Hessian matrix in the course of optimization. However, in contrast to BFGS, where rank 1 updates to inverse Hessian are derived from first principles, our rank 1 updates are learned from data. Finally, the two branches are combined to produce the update of the parameter vector. We demonstrate advantages of our approach on a dataset of classic optimization problems and on a task of physics-based reconstruction of articulated human motion from video. In the first setting, we create a dataset composed of 15 objective functions commonly used for evaluation of optimization algorithms. Each of these functions can be defined for input of any dimensionality. We show a few examples of 2D versions of these functions here on the right. We use dimensions between 2 and 100 for training, and dimensions 250, 500, and 1000 for testing, which gives us a dataset of 45 test functions. In addition, we randomly shift the functions on each evaluation run to increase the diversity of the dataset and prevent the learning-based methods from memorizing the location of the optimum. In our evaluation, we use gradient descent with momentum, Adam, and BFGS as baselines. We tune the learning rate of gradient descent and Adam independently for each objective function. In addition, we compare to the learned optimization method of Metz et al., which is denoted as other factor MLP in the following. Here we show a few example results plotting the objective value at the final optimization iteration averaged over multiple optimization runs that start from random initialization. We use two metrics to aggregate results over a set of objective functions. In the plot on the left, we compare optimization approaches using the performance metric as defined in the paper on best practices for comparing optimization algorithms by Bayravant et al. On the right, we plot the relative number of iterations Optimus needs to reach the same objective value as Adam BFGS and other factor MLP optimizers. Note that Optimus consistently improves over other approaches according to both metrics. Also note that Optimus generally is able to reduce the loss considerably quicker than BFGS. For example, as can be seen from the plot on the right, Optimus is able to reach similar objective value about 10 times quicker than BFGS for the half of optimization problems in our test set. Let us now present the results on physics-based reconstruction of articulated human motion. In this task, the goal is to minimize a loss function that measures similarity of human motion generated via physics simulation and the potentially noisy motion observations acquired via video-based motion capture. In this experiment, we rely on Diffie approach introduced by Gärtner et al. At CVPR 22. The loss function in this experiment is slow to compute, since every evaluation requires to perform physics simulation of human motion. Recall that our approach has a more expensive update function compared to other methods. However, for the task of physics-based reconstruction, the computation done by the optimizer to make an update state is negligible compared to the time required to evaluate the optimization objective. This makes it a good candidate for optimization with our approach. Our first observation is that our approach trains considerably faster compared to our other factor MLP baseline. You can see in the plot on the left that Optimus is able to reach a similar training loss about 5 times faster compared to other factor MLP. We first evaluate the trained model on physics-based reconstruction using motion capture data as input. We separately evaluate on the subset of motions used in training, middle plot, and in a more diverse set of motions not seen during training, right plot. We plot the loss value on the y-axis and the number of objective function evaluations on the x-axis. You can see that our approach generalizes better to unseen data compared to other factor MLP and is able to reduce loss faster compared to BFGS. In the next experiment shown here, we apply our approach without retraining to reconstruction from video and compare to other methods from the literature. Compared to the original Diffie approach that uses BFGS, the optimization with Optimus requires on average half of the evaluations of objective function, while producing results of similar or better accuracy, as can be seen from the mean per joint position error metric. We refer to the paper for further evaluation results and ablation studies.